Welcome everybody. Today we're happy to have Leandro Vendramin from the Vrije Universiteit Brussels, yeah? I don't know. Talk to us about L-Algebras, the Yang-Baxter equation, and algebraic logic.
Thank
Please.
you very much. And thank you all of you for being here. So the plan is to give a talk about, so in general, I work a lot with the Yang-Baxter equation, and I happen to find this sort of uh, similar object, which apparently has some implications in algebraic logic. Is some sort of structure that generalize it generalizes several other structures that you find in algebraic logic, including Haitian algebras and Hilbert algebras. So the plan is to give like an overview about these objects and also a bit about the Yang-Baxter equation in this sort of discrete setting. So the problem that I start with is it was formulated by Drinfeld in the 90s, which is the study of set theoretic solutions to the Yang-Baxter equation. So what does it mean? So in principle, or originally, the Yang-Baxter equation is an equation that you have in the category of vector spaces with linear maps. And of course, you can change the category and consider this equation in some other context. And well, Greenfeld said that in this paper in the 90s, he said that it might be interesting to study this just combinatorially, right? Just using sets and functions. So in the category of sets. So this is how you get this notion, a set theoretic solution, which will be a pair XR, where X is a non-empty set and R is a bijective map satisfying the Brave equation, which is this equation that I wrote there. Not so long after the paper of Drinfeld, there were some papers studying a family or a subfamily of these solutions. The first paper were those of Gateva, Ivanova, and Vandenberg, and also at the same time Ettinghoff, Schedler, and Soloviev. So the first paper, the one of Gateva, Ivanova, and Vandenberg, they were using some sort of ring theory for studying these solutions, and Ettinghoff, Schedler, and Soloviev were using more group theory. But in the end, they got more or less the same results with a different language. So what is the idea? Well, let me first give you some examples, and then I will try to tell you which is the family or the type of solutions you study from this perspective. So the first example is the flip, which for us will be the trivial solution. So just flipping X and Y. This is always a solution for every set X that you have. Then, of course, you can twist a bit the flip. I have a typo there, but you can twist a bit the flip with two commuting permutation, and you still get a solution. These are called permutation solutions, and they appeared in this paper of Drinfeld. Drinfeld attributed these solutions to Venkov, but yeah. And of course, as you can imagine, if you put some extra information on X, then you get more solutions, more complicated solutions, right? For example, if X is the set of integers mod n for some n, say bigger or equal than 2, then, well, you get, like, for example, these two expressions will produce solutions, right? They are interesting and they have some implications in the theory, but I will not go into detail. And more even more interesting is this case. Suppose that X is a group, then conjugation will give you a solution. This is very old, from Hurwitz, like more than 100 years ago. This was found when all these notions were not properly defined. And also you can do some other crazy thing to get solutions, right? The second example is from the 80s, I think, and was found by Wada in a paper where he was trying to get some representations of the braid group coming from solutions, from set theoretic solutions. So there is something that, I mean, it's not so relevant for this talk, but it is for the theory that you can see some invariance, some kind of pattern here. If you multiply X by Y, you get the same result that if you multiply X, Y, X inverse by X. And here the same happens, right? So you have this sort of invariance property for these theoretic solutions. And of course, I mean, there is like a branch of this area where you want to try to get some consequences of this simple observation. Now, which problems we can start with? Well, the construction, right? Like this is challenging enough to be formulated as the first problem. So let's try to construct set theoretic solutions. In particular, let's just try to construct finite set theoretic solutions, right? It's not that you can do this with the computer by brute force. This is too wild problem. So you need some ideas. So first of all, to try to understand which ideas you want to use or which tools, you might want to put like to consider the right context, the right class of solutions. And since if you want to understand this as a combinatorial thing, then maybe a good definition of what combinatorial means would be given by some groups acting, right? So let's say that our solution can be written, our map R can be, which is bijective, can be written as something depending on X and Y in this way and something depending on X and Y in the second coordinate. You will say that the solution is non-degenerate if the sigma X and the tau Y's are always bijective functions, okay? Then you have, in this setting, you have naturally some groups, some permutation groups acting on your set X. Why this particular notation? Well, this is because if you do this in this way, you get that the sigmas somehow are acting on the left and the taus are acting on the right, right? This is, and then, yeah, this is you know, it's nice to write this in this way, right? And the other thing that these papers that I mentioned at the beginning were considering is involutive solutions. Why? Well, because it simplifies a bit the problem and is interesting enough to get a lot of results. So just to simplify my terminology, I will just talk about solutions and I will just refer to, you know, non-degenerate involutive solutions. Okay? So how many solutions you have there? Well, these are numbers of solutions of small size up to isomorphism. I mean, with the computer, by brute force, you can do maybe size 4, 5, and 6, but the others are not so easy. Maybe if you think a little bit and you try to use a bit of math, you can get, and some kind of good programming techniques, you can maybe get to doing some backtracking or something, you can get up to size 8. But then the others are very hard, right? This is something that we did not so long ago with Osgur Akgum and Martin Meret. And we were using constraint programming techniques, which is something that I cannot define very well because I'm not a computer scientist. But is, for me, it's a kind of a black box that does a very, very smart backtracking, realizing or getting some ideas out of the calculations. And it's way better than doing a backtracking algorithm. It's a very, very powerful tool. And it's kind of fancy these days, and you can use it for doing some discrete math, right? It's very useful. Good. So, and this is not just an enumeration. We have, of course, like a concrete database of all these solutions up to isomorphism. So then you can just use the computer to make experiments and stuff, right? Good. So, as I said, why we consider only evolutive solutions? Well, as you can imagine, they are somehow easier than the other solutions, right? In which sense? Well, if you use this notation again, that was the notation I was using for defining non-degenerate solutions. If you use this particular notation, well, a solution is what? A collection of sigmas and a collection of taus, right? But for involutive solutions, you don't need the two sets. One set is enough because you can always get, for example, the sigmas using the taus, right? So, for example, if you want to construct solutions with the computer, this is way easier, okay? So let's say that this is why I start with involutive solutions, okay? Now, okay, so now that I know that I only need half of the permutations to construct a solution, okay, so what do I need to ask to this set of permutations to get an involutive solution? Which are the conditions? right? And this is funny because if you if you try to write down which are the conditions for these taus, well, you don't get much. But if you instead of using the taus, you use the inverse of the taus, you get something. Okay, you get what is known something which is known as a cycle set. What is this? Well, a cycle set is a pair x and a dot, where the dot denotes a binary operation on x, satisfying some properties. And which are the properties? Well, you need this equation, the cycloid equation, which would mean like the Yang-Baxter equation in some sense, and some left, so that the left translations are bijective. Okay, so morally, what I try to say is that if you want to consider involutive solutions, you can just you just need to understand this set of taus, say, and this is more or less equivalent as a cycle set. And you can make this, of course, precise, right? This was a theorem of Rump that he found like 20 years ago, which says that you have a bijective correspondence between finite cycle sets and finite non-degenerate involutive solutions. Okay, and the correspondence is given by this formula that I put there. So the star is the inverse of the tau, and then you have some crazy expression combining the tau and the sigma, or the tau or the inverse of the tau, which is more or less the sigmas, right? So, and this, of course, I mean, I just wrote this in this way, which is somehow what you try to ask the computer to compute. But of course, this is a functorial equivalent. This is an equivalence of categories, right? So you have a notion of morphisms of cycle sets, and also a notion of morphisms of set theoretic solutions, and these two categories are equivalent. Okay, good. So now this cycloid equation is the main topic of my talk, right? So this cycloid is. Oh, sorry, I ran out of battery in my AirPods. Give me a minute. Can you hear me now? Yeah. So,
We can hear you.
yeah, thank you. Okay, sorry. So this cycloid equation, which is this equation x, well, the one that I showed you before, well, is not new. This is something very, very old that goes back to von Neumann and Birkhoff. So at some point in the 30s, they wrote a paper, here is the reference, that they were doing some sort of, I don't know, some new approach to quantum logic, and they were using this cycloid equation. So you have this cycloid equation, and you have like two different paths to go to. Either you can go to the Yang-Baxter equation, or you can go, for example, to algebraic logic, right? And yes, this is where L-Algebras will pop up. Okay, this is what I want to explain a little bit in my talk. So what are L-Algebras? What you can do with them, which are somehow some problems that you can try to solve. And yeah, and the relation with the Yang-Baxter equation is somehow now clear, because it is by the cycloid equation. But they are somehow very different objects in some sense, but on the other, they are very similar. And you can, of course, take ideas from one place to the other, right? So what is an L-algebra? Well, an L-algebra will be a cycloid, so a set with a binary operation satisfying the cycloid equation, but now you need to ask something else. And what is what you want to add to this structure? Well, you are going to ask for some crazy stuff, which in the end will be very well explained by the next slide. So you have a distinguished element, which you call E, okay, satisfying some properties, which are all these properties that I put there, 1 and 2, plus the cycloid equation, of course. So this E is called the logical unit, okay? And all these conditions that I put in 1 and 2 are very weird, because, for example, you see, like the second one tells you that, I mean, will tell you that this guy, the L-algebras don't form a variety, right? So this is somehow worse than solutions, because they do form a variety in the universal algebraic setting, right? So, but what are these two conditions? Well,
this is the thing. So if you have an L-algebra, these two conditions are precisely what you need to put a poset structure on X. So you can say that X is less or equal than Y if and only if X dot Y is equal to E, this distinguished element called logical unit. So essentially, you put the conditions 1 and 2 just to put over the cycloid, so the set with the binary operation satisfying this cycloid equation, to put there a poset in which the greatest element is this logical unit. Okay? So, very good. So, why the L? Why the L comes from logic, right? So, these guys I do algebra. I'm not a logic person, so I don't use an implication for the binary operation. I know that for people doing algebraic logic, it's very annoying not to use an implication and to use a dot. Sorry for that. But yeah, in algebraic logic, of course, you can write this binary operation with an implication, and the logical unit is what you call the truth. And yeah, what does it mean, this poset? Well, this means that X entails Y. So that is some sort of strong implication, right? This is the kind of standard thing in algebraic logic, as far as I know. And yeah, and of course, as I mentioned before, you have some connection between uh, cycle sets and L-algebras, right? If you have a cycle set, you just add to this guy a formal letter, say E, which will be your logical unit, and then you extend somehow the operation. So you do X acting on Y, X dot Y will be X dot Y if X and Y are different, and then you put some definition compatible with this logic, with the fact that you want E to be a logical unit, and you get an L-algebra, which is an L-algebra with a very nice poset structure, right? It's a discrete L-algebra, meaning that if X is smaller than Y, it's because Y is this logical unit, okay? So you have this sort of connection, formal connection, between cycle sets, which are involutive solutions to the Yang-Baxter equation, and L-algebras. Okay? Now, so what you can do with these L-algebras? Well, of course, you can just start trying to construct examples and study them, right? And you find like there are several different special types of L-algebras that are very interesting for one thing or another. But there is one particular family of L-algebras that is extremely nice. Like in say in layman terms, it will be an L-algebra which is also a monoid, and these two structures are compatible, right? So the definition of a self-similar L-algebra is this. Every time you have two elements, you have a third element, which you call Z, with this property. Z is less or equal than Y, and Y acting on Z is X. Okay? And this Z will be just denoted X times Y. Okay? And this is well defined because, well, this Z will be uniquely determined by these properties. Xy is less or equal than Y, and Y acting on Xy is X. And you can prove that this new operation that you get, this xy, is well defined, of course, is associative, and also, the logical unit works as a unit for this guy. Okay, and then you have some extra compatibility between the product and the L-algebra structure. Okay, so this is a particular case of L-algebras, which is of course very nice because it has a monoid structure, right? Apart from the L-algebra structure. And the super nice fact discovered and proved by Rump maybe 10 years ago is that, well, if you have an L-algebra, there exists a unique self-similar L-algebra, let's call this Sx, generated by X as a monoid, right? And also you can embed your L-algebra into this self-similar algebra. So you can always see your L-algebra, whatever it is, inside a very nice L-algebra, which is your crazy L-algebra plus a compatible monoid structure. Of course, this Sx will be an infinite object, right? It won't be a finite, even if you start with a finite one. But you have a lot of math that you can use that in principle, well, it's not clear that you could use or you can use in X, right? This is very, very powerful. Good. In fact, you can go further, right? This um, self-similar L-algebra is also very nice. It's what is known as, or what is called left ore. So it means that it admits some quotient group. This monoid is quite nice. You can define a quotient group on the left, and this will be the structure group of your L-algebra. So in fact, what you have is some sort of canonical map from your L-algebra into a group. This map, of course, doesn't have to be injective. But now you have a group somehow controlling at least part of the structure of your L-algebra. Okay? One thing that you can prove, that was proved by Rumpt, kind of motivated by a lot of work done for the braid group, is that these L-algebras, sorry, these structure groups of L-algebras are torsion-free. Okay? So for every L-algebra, you embed your L-algebra inside a self-similar L-algebra. Then you have a natural map from your self-similar L-algebra into a group, and this group is always torsion-free. Okay? What can you do with this? Well, let's go back to more classical math. So you probably know what is the braid group, right? Let me do like a very toy example. The braid group in 3 strands, B3. So it's the group with 2 generators, let's say R and S, being R is this picture, S is this other picture. So essentially you apply the braiding, you apply a crossing in the first 2 components or in the last 2 components, right? So it's a group with these 2 generators, R and S, and a relation, which is this Coxeter relation. R is the same as SRS, okay? Which is precisely the Yang-Baxter equation, right? So this is the braid group B3. And well, in fact, this braid group B3, it is known that these braid groups are torsion-free. This is something like quite old. There are several proofs, algebraic proofs, topological proofs, and whatever. But in some sense, you can explain this by using L-algebras, by using some sort of algebraic logic, right? So you can define an L-algebra of 5 elements. So you have x, y, yx, and the logical unit, and you put over this set the L-algebra structure given by these operations, right? Then you can prove that, of course, this is an L-algebra. You embed this L-algebra into its self-similar algebra, which is unique up to isomorphism. And then you take this left quotient group and you get the structure group, and you can prove that the structure group is isomorphic to the braid group. And the braid group then is torsion-free. Why? Because it's just the structure group of an L-algebra. So you get some sort of different proof, conceptually somehow different proof of the fact that the braid groups are torsion-free. Okay? And of course, the same holds for all n, right? I just did an example, a concrete example with only 3 strands, but you can do this for all n. So, you can use them. I mean, here you are not saying something new, but you can use them. And they are kind of connected with other topics. So, yes, okay, let's go back to the beginning, right? Where I started my talk with this very naive problem of constructing solutions to the Yang-Baxter equation by computer, right? Up to isomorphism. So, and I know that L-algebras are very similar because they also satisfy the cycloid equation. Can we construct final L-algebras of small size? Of course we can. So we just need to translate this into a combinatorial problem suitable for constrained programming techniques. And this is what we are going to do. So this looks very, very ugly, but it's very easy. So essentially you are gonna put, so your set will be always a finite set from 1 to n. So the binary operation will be a matrix, and n by n matrices, and the entries will be numbers from 1 to n. And these 5 conditions that I have here are just precisely the translation of all the formulas that I need to define an algebra into just matrix coefficients, right? Of course, I need to put where the logical unit will be. I can take the 1 as the logical unit or the n or whatever number I want. It's kind of convenient to take n, the last one, because, then you have like a good I mean, instead of using, for example, for the symmetries, the full symmetric group, you just know that, the symmetries will fix the logical unit. So instead of considering some crazy subgroup of Sn, you just consider Sn minus 1, right? Fixing the last element. So this is why you put the logical unit in the last step. And of course, you can prove that there is a correspondence between finite L-algebras and matrices satisfying 1 to 5. Of course, you can make this very, very precise mathematically, but it's not really needed, right? You just need to reformulate the definition into something that you can put inside the computer. And of course, the kind of the tricky part is the isomorphism, right? So you want to understand isomorphisms of L-algebras into this language with matrices, with these crazy matrices. And well, this is done by defining an equivalence relation. So you will say that two matrices are equivalent. So morally, it means that they represent exactly the same isomorphism class of, up to isomorphism, they are the same L-algebras. And this is, well, this equivalence is defined like this. You have a permutation in Sn minus 1, so fixing the logical unit, which is something that, of course, you need to ask for a morphism of L-algebras, satisfying this, which, is nothing but just a relabeling. It's just this, right? Because what would be an isomorphism of L-algebras when you look at this in these matrices? Well, it's just a relabeling, right? You just shuffle the numbers and then permute columns and rows as you have to do. And well, this is how you just define the equivalence relation. And then, of course, you can indeed prove that two L-algebras are isomorphic if and only if the corresponding matrices are equivalent in this sense, okay? So with all of this, you can just put this in the computer and compute the L-algebras. But let me show you a concrete example, very naive, very small. So you have X is a set with 3 elements. So you have X, Y, and the logical unit. This is how you put the L-algebra structure on the set. You can check that this is an L-algebra. And you can compute the MX. So you need to label the elements of X, right? So let's say that X is 1, Y is 2, and the logical unit is 3. Remember that I was using this convention, right? That the logical unit is the last element. This is fun. Then the L-algebra is just this matrix. Okay? Very good. So with this, you can put this in a computer in using constraint programming, some software of constraints, and then you get numbers. So you get up to size 7, you can do it, right? And you get that the number of L-algebras really grow quickly. But the one in size 8, you cannot do directly, right? You need to use something else. It's not just a matter of giving this to the computer and the computer will just return the number of the set of all solutions up to isomorphism. This you cannot do. And this is something that we did with Karsten Ditzel, my postdoc, and Paula Menchon. So we just not only took care of these cases, which were rather easy, but also with size 8. And there you need to use a lot the structure of the L-algebra, right? Like L-algebra theory in some sense. First of all, you split the problem depending on different posets and then try to use somehow the structure of the poset in each case, okay? and maybe even going very deep into some cases that were very, very hard. So this is highly non-trivial size 8, right? So yeah, this is what we did. So we got a very big database of these L-algebras. And what you can do with that? Well, now that you have a database of all L-algebras, then you can start, making experiments, conjectures, comparing this with other things, and so on. So this is something that we did. For example, if an L-algebra is said to be linear if the partial order is a total order. This is one possibility, right? You always have a poset structure over X on X. Well, you put a name in the case that this is a total order, which, is not very, doesn't happen too often, right? And then what we did was okay, let's count how many L-algebras are linear in our database. And we found that, it was kind of easy to count them because you could count them with Bell numbers, okay? This is very, very well known. The sequence of Bell numbers is this one, 1, 1, 2, 5, 15, 52, okay? So we had a conjecture, right? Okay, you can count linear L-algebras using Bell numbers. And indeed, we could prove that. We proved that the number of isomorphism classes of linear L-algebras is given by Bell numbers. And the proof somehow uses what the Bell number is, what the Bell number is counting. A Bell number counts the number of partitions of sets. Okay, so you have a set with 3 elements, you have 5 partitions, which are this one. Okay, and precisely this is what we use to count some inductive argument to count how many L-algebras you have by some induction. But our proof, well, is an induction proof. It doesn't give you an explicit bijection between L-algebras and orders. The L-algebras on this order set and partitions of your set, right? This is something that we couldn't do. We got a proof by induction, but it's not an explicit bijection. In combinatorics, that are somehow you like counting, but also you like bijective proofs. We couldn't get the bijective proof. Okay, so this is still open somehow. And then, we did a lot of these, like experiments and then get numbers and conjectures. Of course, a lot were wrong, but we have another one which was quite fun, which is this one. So an L-algebra is of type F. I mean, in the theory of L-algebras, this equality has a name, and this other equivalence has a name, right? But for this talk, I'm just calling this type F. So you will say that an algebra is of type F is if these two properties which are satisfied. This one is called symmetric, and this I don't remember. Okay. Okay. So how many L-algebras of type F are there? Well, the conjecture is that you can count them by Fibonacci number. This is why the F. Okay, but we couldn't prove that. We could, extend our computations, like computer calculations, to get some more numbers because we didn't need to construct all the L-algebras, just those satisfying these equalities, and we could go farther with the enumeration. So it seems that the conjecture is true, but we couldn't prove it. Okay. It would be nice because, of course, you know how you get Fibonacci numbers. So there should be some sort of inductive process to do this, right? But yeah, we couldn't prove. So this is a conjecture that we have that would be nice to see proven. And in algebraic logic, there are people study these, say, universal algebras with a set and a binary operation satisfying some properties, right? And one important and big class of these algebras are these Hilbert algebras. And well, Hilbert algebras are just included in L-algebras. Those are L-algebras. You can prove that a Hilbert algebra, which has a crazy definition, is nothing but an L-algebra satisfying this distributivity. So, like for free, what we did produces the list and a database of Hilbert algebras up to isomorphism. And this is the sequence of the number of Hilbert algebras up to isomorphism, which, as far as I know, this was not known before, right? Now, if someone is interested in Hilbert algebras, well, you have a database with a lot of Hilbert algebras to test your conjectures or make new conjectures or experiments or whatever, right? Of course, we also wrote some functions to play with this database. Otherwise, you cannot access to the database, right? But yeah. Good. So yeah, and just something that we experiment with the L-Algebras with the database. We got some other property that looks very nice, right? And yeah, so that somehow produces or suggests that there is some sort of geometric theory of L-algebras. So L-algebras have ideals. So what is an ideal? An ideal of an L-algebra is a subset with some properties, and the properties are there from 1 to 4. Of course, I mean, you can imagine what an ideal should be, right? So the logical unit form an ideal. The full L-algebra is, of course, an ideal. Intersection of ideals is an ideal. This is a notion that works really, really well, right? And yeah, this was also in the first paper on L-algebras written by Rump. He proved that, of course, ideals are the same as congruencies for which the quotient will give you an L-algebra, right? Which is what you expect. Here is the precise description of the correspondence between ideals and congruencies with that property. That's fine, right? So yeah, you have a good notion of ideal, which allows you to quotient out an L-algebra, okay? And yeah, and you can say that an L-algebra is distributive if, well, you have this distributivity with respect to ideals, right? So, of course, as usual, the intersection of ideals is an ideal, that's nice, but union of ideals in general is not an ideal, so this is why you consider here the joint, which is, the ideal generated by the union, right? Very good, because, yeah. And Hilbert algebras are known to be distributive. This is. I mean, you can expect this somehow because of the distributivity you have on the elements, and you can indeed prove that you have this distributivity with respect to ideals. And we conjectured that L-algebras were distributive. So we computed all the ideals of all the algebras of our database, and made the conjecture that every L-algebra is distributive, right? And indeed, using the things that I mentioned at the beginning, using this self-similar algebra that covers your L-algebra, we could prove with Rump that finite L-algebras are always distributive. This is a general property of all L-algebras, at least finite, right? I don't know if this is true for infinite, but everything here was for finite, so yeah. And we proved with this with Rump, which is kind of nice, right? Because it puts everything in a different somehow perspective, right? Because now you could try to do some sort of geometry of L-algebras, trying to study the spectrum. So this set of ideals or particular sets of ideals, right? Ideals. There is a notion of prime ideal. You could study the set of prime ideals or ideals that are generated by a single element or whatever, right? All because of this theorem, which, as I said, follows from. It's not very hard. It follows from the existence of this self-similar algebra. And then what you can do with this, well, as I said, you could study the spectrum of L-algebras as a very, very general problem. Like, for example, computing the spectrum in particular classes of L-algebras, like linear L-algebras or whatever, right? You could also try to understand what simple L-algebras mean. This, I don't really know what to say about this because, if you go to the database, you find that a classification of simple L-algebras, like naive classification, might not be possible, right? Because at least from the database that I have, which is up to size 8, more or less half of the L-algebras are always simple. So yeah, probably, I don't know. Either the notion of simple is not the right one, but why? Because simple means I don't have quotients, so it shouldn't be so bad. But yeah, half of the L-algebras seem to be simple, or more or less. So yeah, would be nice to understand what not the classification maybe, but something more about simple L-algebras. And this is somehow motivated by this distributivity property that we proved with Rump. So I think that this is everything what I wanted to say. Thank you. It was a bit short, but yeah, thank you.